Hello everyone, my name is Hamed. I'm excited to present my research entitled of VREX, a requirement engineering framework for Vision-Centric Intelligence in AI-enabled software. V stand for Vision-Centric Focus, RE for requirement engineering, X as a flexible placeholder for domain knowledge extraction, dataset evaluation, and data selection, and also AI model evaluation. So in our upcoming slide, we refer the requirement engineering as a RE. I refer our framework as a whole as a VREX. So in this research, I aim to address the gap in the integrating RE into AI systems. This work focuses on the creating a structured approach to align domain knowledge, dataset, and AI model with the real-world requirements. So I am fortunate to have the guidance of my advisor, Professor Muraraimi, and the support of my committee members, Dr. Al-Huisun and Coop. So now let's dive into the outline of this presentation. Here, first we go through the introduction, motivation, and problem statement. We have to have a formal problem statement. Then we present our research question. Then we try to framing the approach from the literature review to our framework VREX. So then we discuss over the requirement engineering for AI-enabled system, REIS framework. Then we discuss over the semantic augmentation and generalization engine, SAGE. Then we have a concept augmentation and dataset evaluation. After that, we discuss over the black box evaluation of the visual perception in AI-enabled software, short in VIS, and go for the white box evaluation. VIS stands for white box evaluation. And then we discuss over the ongoing research and our challenge. So these, I will repeat every component again and try to use the complete name, but sometimes I will refer to the short version of them. But if you have any question about the name exactly, I can explain you. So let's dive into what is the difference between the software design in the conventional software and AI-enabled software. So in software design in conventional software follow the built-in requirement specification, and those specification mirrored into our source code. So we have already defined requirement specification, which define the functionality and guided our design. So at the end in evaluation step, software success depend on how those code meet the requirement specification. In contrary, in AI-enabled software design, so we mostly rely on the training data, not the explicit specification. We have a kind of specification, but it's not it's implicit already. So then behavior is learned rather than directly programmed. So we provide the data and try to train the model to learn the behavior and patterns. At the end, the success depends on not the quality and the completeness of, so success depends on the quality and completeness of the training data. There is no clear specification to test against those requirements. So we said that we can see here those differences visually. We provide the specification as the programmer to code those specification. Then we have some set of the specification in the beginning. Then we run those program or code against those specification. So while in the training in the ML software, we have an example as a data set. Try to train the model, and those data sets all usually have a incompleteness or some problem with them. So actually we said garbage in, garbage out always for when we providing the data sample. So our performance in the AI-enabled software highly depend on the quality of the example. So the absence of the predefined specification makes it challenge to going to measure whether the system is behaving as expected or not. So we said that in the next slide, we are going through the challenge in validation, in evaluation of for AI system. We started with an example of the sampling requirement. We're saying, hey, we expect that the system detect the pedestrian within 0.5 mile with an accuracy of 95%. Even this simple requirement have some challenges. The first challenge is of defining the concept. What is exactly concept of the pedestrian? Does this include the individual in the wheelchair, or children or people carrying object, or people on the scooter? Variation of the definition complicate how this requirement is implemented. So second challenge is about the data set challenge. Does the training data include all those variations? So if not, the model may fail to generalize, reducing its effectiveness and accuracy. The third is the evaluation complexity. So even if the data set diverse, we need to check how will AI truly understand what a pedestrian is. AI model learn the pattern from the data, but sometimes they pick up the wrong pattern. For example, if mass pedestrian appear near to the crosswalk, they may think that the crosswalk is an attribute of the pedestrian, and then model may fail in the desert to detecting the pedestrian crossing the street. So it's important to note it is important that AI making correct decision based on actual pedestrian feature, not an unrelated pattern. So it is important to note also we are not focusing in the image quality issues, like lighting or camera angles, are focused on the how will pedestrian concept or other concept that we are going to test for our framework defined and represent in the data and evaluated the model understanding of that concept. So know that we have explored the sample requirement and its challenge. Let's move on to the motivation and research gap in the AI requirement. So here are, as we mentioned earlier, key challenges about the specification gap. There is no formal method of defining complex concept like a pedestrian, leading to an ambiguity. The second challenge that drive our research is a data set misalignment, training data sometimes lack of diversity, causing a bias or poor generalization. The third challenge also we mentioned earlier in our example is an evaluation challenge. No standardized benchmark to assess the AI performance against the domain needs. So here is why RE is critical for AI. So RE can help us to bridge the gap between the domain knowledge and AI. Also, RE practice can reduce the ambiguity by ensuring AI models follow clear and well-defined requirements. Also, RE can help us to guide AI development through the structure evaluation. We said that we are going to answer that how RE address these challenges. So for the specification gap, develop a semantic model and a structured ontology to clarify ambiguous concept and create a well-defined actionable requirement. RE can help us to close the gap or solve the gap. For dataset misalignment, also RE methods and practice can introduce tools to evaluate data gap, applies augmentation strategies, and ensure dataset represent all relevant domain variation. So for evaluation challenge also, we can leverage the RE to establish a domain-driven test framework to serve the benchmark for assessing AI system independence of the training data. So with talking about these challenges, now let's define a formal definition of our problem. So the formal given an AI-enabled system learning a domain concept called C from the training data set of D using a model, AI model called F. The objective is to ensure that the learned representation C had aligned with the real world expectation. So here we have tried to address the specification gap which is the D here is a distance measure, where D is a distance function measuring the deviation. Delta specification is the divergence between the intended domain knowledge of C and the learned representation of C hat. So large delta specification means the model failed to capture domain nuisance. So also we have a data set misalignment. We have to measure the data set misalignment with the delta data, which is again D is a distance measure, where here D is also training data, probability of the training data distribution. The data set, they may not fully represent the real world distribution, which is the probability of real world, which leading to our bias. So also we have an evaluation misfit. We call it delta evaluation. It's trying to distance the measure the distance between the model prediction from the requirement, where FAD represents the model prediction, and a standard metric may not adequately capture compliance with the domain requirement of R. So our objective here is to ensure reliable concept representation to minimize the combined effect of these inconsistencies. So the way we said that we are going to frame our research question into the three core research questions with two sub research questions, and also we are going to map these research questions all into our objective. So our first research question is, how can RE principle be adopted for AI-enabled system? How do existing RE practice need to evolve for data-driven and inductive AI model? How can this practice address lack of explicit requirement in AI model? The second research question is that how can integrating RE practice into AI development workflow improve the AI-based software and understanding of its domain? So it's led to sub-question that how can RE improve the AI system alignment with the real-world domain-specific concern? How this embedding domain knowledge help to identify and resolve the data set? The third research question also is here to how can AI-enabled software be systematically evaluated against the domain specification? We have two also sub-question. How can testing be guided using a benchmark tied to domain requirement? How can AI behavior align with the specified domain knowledge? So here we try to frame our research question into objective, a simpler research objective. So objective one is here to domain-driven requirement extraction, transforming implicit domain knowledge into a structured AI consistent. The second objective here is the semantic data alignment and augmentation, ensuring that the data set represents real word variation through the augmentation. And third objective here is the requirement-driven evaluation, which is establishing a structured benchmark for AI evaluation. So each objective is operational by two dedicated components, which we explain them further in the next slide. So here also again we have a map between the objective and the developed component so far. So first objective map, which is the domain-driven requirement extraction, map to the requirement engineering for AI system, we call it REIS. Also there are another another component that help us to realize the objective one, which we call it semantic augmentation and generalization engine, SAGE. Also to realize this objective two, we have a conceptual alignment dataset evaluation calling K, and we have a visual conceptual alignment and dataset evaluation calling VSK. To realize objective 3, we have also two components. First one is a BIS calling black box evaluation of the visual perception in AI-enabled software. The second one is a white box evaluation for visual perception in AI-enabled software. So know that we defined the problem and discussed the motivation, research question, and our objective. and map of objective to component, let's go through the related work and propose our approach. So, no, here we frame our research question, begin by zooming out to present a high-level overview of the literature review, and then go for the defining our objective. Then we will step back and provide a zoom in related work for each component. So this slide shows how we position our framework VREX within the broader REA for AI research landscape. We reviewed the field across the 5 areas: elicitation, specification, and dataset quality, evaluation, and non-functional requirement, and group peer work into subcategory aligned with our 3 core objectives. So for objective 1, which focus on the domain-driven requirement extraction, Ahmad and collaborators highlight how hard is it to formalize domain expertise. Pri and collaborators also propose a formal structure using Zave-Jackson framework, but don't apply it to real-world system. Wilizimir and collaborators also provide a helpful catalog of domain concepts, though without the method for applying them. For objective 2, relates to the dataset alignment and augmentation. Most previous work like Balaur and Chen focus on the fairness, completeness, or data size, but they rarely connect the dataset to domain requirement. Nakamichi and its collaborator also go further and showing that the data quality must be defined in terms of coverage and distribution, especially for machine learning software. So finally, for object 3, Rajavali and collaborators point out that the lack of domain specification evaluation method and Sang and collaborators bring in the real-world scenario mainly for the autonomous system. Gulpaigani and the collaborators also emphasize aligning AI with the legal standards like the Europe AI Act, but benchmarks often aren't tied back to the domain requirement. Together, this work shows where the progress has been made and where the key gaps remain. VREX is designed to bridge the gap, linking the requirement extraction and data alignment and evaluation in a clear, objective-driven way. So know that we have mapped where existing work stands. Let's look at the key idea that drives our VREX forward. So here we have 4 key ideas. First one is that the AI requirement must be explicit and domain-driven. Traditional RE measure the predefined requirement, but AI lack of clear specification. My research ensure that the requirements are structured around the domain knowledge rather than being implicit. Second idea is developing a structured method for hard-to-define concept. Third key idea is ensuring dataset alignment with the domain knowledge. Fourth key idea is integrating requirement into AI evaluation. So we put all these 3 all of these 4 idea in the diagram that shows that how each of them may interact with each other. We go in detail in upcoming slides, but first let's go through the objective we discussed here and we talk about them much and have a clear definition of the objective. What is the objective 1, 2, and 3? So first, let's dive into the objective 1, which is foundation of my approach. To begin, this is the focus on the translating implicit domain knowledge into a structured requirement. So AI-enabled software often operate in a complex domain where the requirements are not explicitly defined. My method is to extract this knowledge and organize into an actionable requirement. Next, the goal is to define a constraint for the dataset and model based on domain knowledge. These constraints ensure that the AI system align with the real-world expectation for their domain. So constraint we say typically include the concept persons constraint, attribute constraint, and also contextual constraint, ensuring that the concept appears in context, semantic, or spatial relationship. So next goal is the additional. This is critical for specifying hard to specify concepts such as ambiguous term like a pedestrian. By leveraging domain knowledge, we create a structure defined that can guide the dataset preparation and the model development. Finally, we generate a benchmark to guide the dataset preparation, ensuring that the data reflect the domain specific need and expectation. To make this concrete, we have included a simple pseudocode that shows how this process works. This function starts by looping through each key concept from the domain knowledge. For each concept, we extract this relevant feature from the training data, define the constraint, and then organize them into a structured requirement. These outputs are used to guide towards dataset construction and evaluation and model evaluation also. So having grounded our approach in the domain knowledge, the next step is the aligning this with the dataset itself. So here we discuss over the objective 2, semantic data and data alignment and augmentation. We have a 3 steps for that. We have to ensure that the dataset align with the domain specification requirement, address the gap using the data augmentation technique, at the end improve the dataset augmentation strategy, ensuring the comprehensive representation of the domain concept. Here also we have a simple pseudocode that shows that the key step, this function goes through each requirement and check if the training data is missing any important domain concept. If something is missed, we generate the systematic synthetic data or use the augmentation technique. For example, retrieval from the existing sample to fill the gap. Once the data is aligned with the domain, we need to evaluate the AI system against this requirement. This leads us to objective 3. So for objective 3, we are going to establishing a structured evaluation benchmark from the domain requirement to ensuring AI model meet the predefined constraint instead of relying on general evaluation method. Also, we identify gap between the AI model output and the domain requirement for defining a specification. So also here you can see a simple pseudocode that shows that how a step is going to be realized by our framework. So the function tests the test the model on a structured test case built from each requirement. Then it checks how closely the model prediction match the expected behavior using constraint and benchmark. Know that we have seen how objective is tackled. Let's take a step back and see how these goals map to the component of the VREX and related work. First, we are going to have an objective to component. Objective 1 is realized by REIS and SAGE. Here also objective prior study like the Rahimi, Banks, and Saleh identify concept ambiguity and the traceability challenge, especially for vague term like a pedestrian, but those afford lack of the operational method. REIS closed this gap by formalizing this concept into a structured ontology. SAGE also further bridged the conceptual visual gap by turning abstract specification into actionable data level criteria, something missing in the earlier work. So also for objective 2, it's realized by 2 component K and V-scale. Here we are going to address the semantic data alignment, while prior work like Ahmad, Shin, and Google pair discuss the data quality or bias. They didn't offer a way to validate dataset against the structure requirement. Kate changed this by benchmarking dataset completeness using the RE artifacts. With Kate also built on top of Kate with the human in the loop, adding interactive inspection of grounded in RE logic. So for objective tree, which is consists of the two component BIS and VIS, also we are going to center on the requirement-driven evaluation. Existing model rely on the generic metric on or silencing maps. BIS instead performs zero-shot or black box auditing using a semantic similarity, but with the domain constraint domain constraint in the loop. And VIS goes deeper in the concept internal model behavior to ontology. Is connect the internal model behavior to ontology guided expectation, offering a formal RE way to diagnose and evaluate the perception. So VRX doesn't just respond to known problem. It's operational RE principle across the specification, dataset, alignment, and evaluation in a way previous work never integrated. Know that. Let's look at how these components fit together in the high-level architecture of the VRX. Here you see a high-level overview of our framework. It's started by the REIS and the SAGE is try to extract the knowledge and forming a formal benchmark on requirement engineering. Then we use that for the data set evaluation, curation, and a model evaluation. So we have that. After that, we have those requirement benchmark. We evaluate the data set against that benchmark. Also, we can use it to evaluate the model itself against the requirement engineering benchmark. These all together have also connection. For example, VIS can use the K to find a missing part or missing variant in the dataset and asking for the augmenting dataset based on those evaluation. Know that we have a high-level overview of the how we fit together this component. Let's go through each of these components and discuss over them. So here, first we are going to discuss over the requirement engineering for high-level system, REIS framework. As we mentioned earlier, REIS tackles the challenge of the extracting structure requirement from the informal domain knowledge. These results are published in the RE journal paper titled "A Multi-Level Semantic Web for Hard-to-Specify Domain Concept Pedestrian in ML-Based Software." This work is a foundational. It's built a semantic structure for hard-to-specify concept like a pedestrian, which the ML models often learn implicitly and inconsistently from the raw data. So RES is not the concern with the model training. It's focused on the specification design. It's transform noisy domain insight into formal machine-readable semantic that outline the concept variants like a children, elderly individual, or people in the wheelchair. So this semantic web is meant to guide how we judge the dataset coverage and clarify what requirements should mean for ML-based system. REIS address the three main challenge: concept ambiguity, vague or socially constructed term like a pedestrian, lack of formalization, RE output that aren't already currently, and unstructured knowledge, currently domain context scattered across the informal sources. What REIS contribute? A structured pipeline for the specifying hard-to-specify concept, a semantic requirement for AI-oriented evaluation, and a foundation for judging the dataset completeness. In short, REIS build the specification, not the dataset. It's bring the RE techniques into the AI loop to shape what domain alignment should look like. So next I will walk you through how this semantic pipeline works. So here you can see we have started from trying to shape a multi-level semantic web for AI requirement. We start with the concept augmentation extraction, related term for a hard to specify AI concept. For example, pedestrian. We look at the existing domain knowledge sources like a Wikipedia, Twitter, or any online sources to find the related words or term to a pedestrian. Then we have a topic discovery, which clustering the terms into the meaningful high-level ontologies. After that, we create a semantic web on top of that. So structuring relationship between this concept into a multi-level hierarchy. After that, also we have a detailed concept expansion, refining the relation through using the analysis of like a part of a speech tagging. Then we have to find the dataset gap identification. So using the semantic web to find the missing concept into the AI dataset. At the end, we have also dataset augmentation, expand the dataset to cover missing variation. Then we perform the augmentation and then have some evaluation on the AI performance before and after dataset augmentation. So in this study, we applied REIs to assess the semantic coverage of multiple benchmarks. The dataset, our analysis revealed that the city person and the wider person align better with our pedestrian hierarchy than COCO, highlight the significant gap in coverage, especially for the underrepresented pedestrian type like a wheelchair user. While REIS itself does not perform augmentation, its specifications serve as a semantic benchmark to identify what is missing. This benchmark later guides SAG whether the semantically informed augmentation was performed. In follow-up experiment, model trained with the SAG guidance showed that substantial gain. For example, map 50% value improved from the 58.5% to 90%, and recall increased significantly when tested on the held-out wheelchair pedestrian image. So REIS thus lays the foundation. It transforms vague domain term into structured testable specification. This is a critical step toward the VREX and E4AI, enabling automated evaluation of dataset alignment and model expectation. The impact is clear. By formalizing semantic requirement, we set the stage for the building trustworthy and the generalizable AI system, especially in the safety critical domain like autonomous driving. Note that we discussed over the RES, which is our foundation of our work. Let's go through the semantic augmentation and generalization engine. Here, as we mentioned, while RES built a structure understanding of domain concept, SEAG take the next step, ensuring that these specifications are reflected in the actual dataset. This outcome of this component also published in a paper entitled of Kane 22. Title of our work paper was a method was the improving generalizability of the ML-enabled software through the domain specification. So if REIS asks what is the pedestrian, SAG asks that does your dataset actually include all kind of the pedestrian your system need to see. SAG goes beyond the data augmentation. It transforms a specification into an actionable dataset evaluation and the augmentation framework. And instead of blindly collecting more data, we use SAG to identify semantically underrepresented pedestrian type, target the data collection for missing variant like a wheelchair user, evaluate the data completeness with respect to the real world expectation, and Also, SAG contribute in three ways: from the specification to data, turning the abstract specification into dataset alignment criteria, semantic guided augmentation, adding what's missing, not just more, generalizability by design, improving the model performance on the rare case by aligning data with the domain semantic. We evaluate these through two core questions: how accurately can we define the partial specification for hard to specify concept? How useful are those specifications for improving dataset quality and model generalizability? Think of SAG as putting REIS into practice, where the formal specification drive practical improvement in how dataset support AI learning. So, know how turn to SEG operationals, the specification created by the REIS, and what's impact that has on the model performance and generalization. This process begins with the domain knowledge extraction, where we mine the textual and visual sources like the Google Books, Wikipedia, and the pedestrian image dataset to identify concept-relevant attributes. These attributes are formalized as a partial specification using subject-predicate-object structure, like a pedestrian has a wheelchair. These specifications extend what REIS define and make them actionable. With those specifications in hand, we assess the dataset completeness by checking whether each dataset adequately represents the full semantic specification of the domain concept. This reveals what's missing, such as underrepresented variation like the elderly pedestrian, kids, or wheelchair user. So then come to the key contribution of SEGE, semantic augmentation. Instead of the randomly adding the more data, we selectively include only missing concept variant identified through the specification. This creates a targeted specification aligned dataset. Finally, we evaluate the effect of the effect. The results are compelling. Model trained on SAG augmentation dataset show up a 7-point increase in the map value. They were more robust to domain shift, generalizing better across the unseen context. Our semantic benchmark also validate the specification coverage with the 75% precision and recall. The takeaway of is that the SAG makes RE actionable. It shows that when a specification guided dataset construction, we got a model that are not just more accurate, but more robust, reliable, and aligned with the domain expectation. So, getting idea from the REIS and the SAG, we see that there is a missing research area, which is we call it concept augmentation and dataset evaluation. We get those idea from the REIS and SAG and try to develop independent component called CADE for dataset evaluation. So, following the SAG, which support the dataset augmentation using partial specification, now we turn to the question of the dataset completeness. CADE result also published in the RE conferences in 2022 entitled of the CADE, the missing benchmark in evaluating dataset requirement of AI-enabled software. Here we introduce the CADE in detail, a framework designed to evaluate how well a dataset represents the domain knowledge is meant to cover. Unlike the other method that focus on data collection or augmentation, CADE starts by asking a fundamental question: is the current data set already sufficient or not? So our motivation comes from the safety critical domain like autonomous driving, where biased or incomplete data can lead to real world failures. Despite the progress RE and AI there still no standard method to checking whether the training data set include all key variants of the domain concept, especially for hard to specify concept. Kate addressed this by shifting focus from the data generation to or data collection to the data evaluation. So it's work in the 5-step, extracting domain knowledge. We started by identify concept variation using source like a Wikipedia, visual dataset, and knowledge base. Building a semantic benchmark, this serves as a structured reference for what the dataset should ideally contain. Then we have a dataset interpretation. We use the AI tools like object detection and NLP to extract what's actually present in the dataset. Then we have automated evaluation process. Kate compared the dataset concept against the benchmark, quantifying the coverage and identifying blind spots. Then we have the identify the dataset gap. Finally, it surfaced the specific variation that are missed, those critical for the generalization. So Kate filled a major gap in RE for AI, providing a requirement to audit the dataset before training. Instead of adding more data blindly, it tells us whether what we have already meet the domain concept expectation or not. So here we present our the key finding and add contribution. Kate introduced a structured benchmark to evaluate dataset completeness against the domain specification, unlike the method that focus on augmentation. Kate assess the dataset quality before the training, helping reduce the reliance on the arbitrary or heuristic data construction. It filled the missing gap in RE4AI by providing a concrete reference point for the validation dataset against the existing requirement. Compared the prior work, Kate doesn't define new requirement or generate additional data. Instead, it's evaluate whether the current dataset adequately represent the domain need, bridging the disconnected between the RE artifact and the AI data pipeline. Applied to city person and Eurocity person, Kate revealed that up to 60% of the key vehicle related and 48% of the pedestrian related concepts were missing, especially rare but safety critical cases. Manual validation showed that around 75% alignment between the Kate generated specification and the expert expectation, confirming that the method revealed the relevance and the accuracy. So now that we discussed over the Kate, go for the model evaluation on the BIS and VIS. These two are also closely related together. Here we discuss the BIS component, which result also published in another paper called named BIS, an automated process for black box evaluation for visual perception in AI-enabled software against the domain semantic. It got published in 22 in the automated software engineering conferences. As we discussed, AI models are often trained on the massive data set, but we don't have a structured way to evaluate what they have actually learned, especially when it's come to subtle or rare domain variation. This becomes a critical in vision-centric system. We're missing a concept like a pedestrian using a wheelchair can have a real-world consequence. BIS addressed this by introducing a black box evaluation process. It used a semantic benchmark grounded in the domain requirement to test the model perception accuracy. So crucially, it does this without accessing the model internal. This approach fills the key gap. If it doesn't augment the data or extract the requirement, it systematically audit model behavior from the outside. It's helped to identify mismatch between what the model sees and what the model domain logic expect, revealing the dangerous blind spot and generalization failure. Next, we look at this evaluation is done and what insight it's provide. Before going to evaluation, let's go through the methodology. of the BIS is extracting domain semantic, then use that domain semantic to dataset and model perception evaluation. Then we have concept coverage in the dataset and also in the model itself. And then we provide some feedback, evaluation feedback to user. So after that, we get this feedback. BIs contribute in, we find that the BIs contribute in three key ways. First, it is enable the black box evaluation. We can assess the what model understand without the internal access. Second, it's introduce semantic-driven testing, where the model outputs are the compared against the structure concept specification. And third, it's filling the gap in current evaluation practice by focusing on whether the model truly grasps the domain concept variation. So what makes BIS stand out is that the actionable insight it delivers. In both automotive and aviation domain, it identified major gap between the model predict and where the domain required. So for pedestrian detection, up to 45% of the key variants, like a wheelchair user or children, were missed. After the retraining, with those missing cases, model accuracy improved by 36%. In aviation also, model failed to capture 28% of aircraft-related variation, and retraining improved the semantic alignment by 28%. So bottom line, BIS doesn't just evaluate, it reveals the underrepresented concept and provide the pathway to correct them in the model understanding. So making AI more consistent and domain aware. So also next we are going to do white box evaluation of the visual perception AI-enabled software. This outcome of this component also published in the 2025 in the paper entitled of the AI-driven requirement engineering framework tailored for evaluation AI-based software. So here BIS built on the idea that it's not enough to evaluate what AI outputs. We also need to understand how it's reasoned internally. While BIS focused on the black box testing, BIS introduced the white box approach that that combine the requirement engineering with the explainable AI. The goal here is to ensure the model internal focus align with the structured domain concept, not just the pattern in the data. So this is critical for safety critical domain, where the misaligned attention, like overlooking a wheelchair user, can have a severe consequence. BIS also address this by going inside the model and checking whether the attention match what the domain knowledge expect. So it's work in six steps. First, we extract the domain knowledge to define the core attribute. Then we map both the specification and model focus into a shared embedding space. Then we measure the specification perception distance, how far off the model focuses, and then we generate the attention score for missing or weakly recognized topic. Then we use the external sources to retrieve the visual example for those gaps. Finally, we augment the data set with the targeted instance to improve the alignment. So VIS bring the RE and XAI together, not just explain, but correct the model behavior from the inside out. So in the next slide, we are going to also present our key contribution and finding results. Also here you can see in this image, before using the VIS, attention varies. For example, here a woman in the, it's generated caption like the woman in the mask riding a bike. So it couldn't detect the wheelchair. after training and changing the attention by inside of getting the attention, a woman in the wheelchair with a face mask is on the crosswalk. So also for this image, also you can see a woman pushing a motorcycle in the rain, and then it got changed to a homeless woman walking in the rain. So it's based on the attention and the caption and so on, we find that how it got improved comparing to other researchers. We can say that VIS enhanced the AI model alignment with the structure requirement, improving the perception accuracy across the ontology benchmark, dataset caption, and the human-generated description. It also boosts the recognition of unseen concept variation, improving the generalization to rare cases like a wheelchair or a typical aircraft. So this is driven by its AI-based evaluation. VIS use the attention analysis to detect where a model focus and diverge from the domain expectation and guide the targeted refinement to correct those gaps. In our test, VIS significantly improved the performance for pedestrian side rose by 67%, spice rose by 43%, and semantic similarity goes from the 29 to 38 for pedestrian. In aircraft, domain airside improves the 27%, and spice goes 20% up, and similarity goes from the 48 to 54. This result confirmed that VIS strengthens both perception accuracy and the alignment with the formal specification. Overall, VIS provide a structure or integrated refinement loop for evaluating and improving model behavior in the safety critical domain. So here, in summary, I'm going to, in this slide, provide the summary what I've done so far in all of these components. In the paper one, we extracting domain knowledge for AI. So we build a semantic web for AI concept. Then we have a requirement-driven dataset augmentation method, align the dataset with the real-world variation using the extracted domain knowledge. In the component 2 or paper 2 also, we have a specification-guided AI training using partial specification to ensure dataset represent the domain knowledge. And also, we have a semantic augmentation over a random expansion. In the third component, we have a requirement-based evaluation for dataset. Also, we have an early gap detection on the dataset. In the component 4, BIS AI evaluation, we have an AI evaluation without the internal access. Also, we have some feedback for guided AI retraining and reducing AI misclassification. Also for VIS, we have AI-driven AI model validation. Also, which enhance performance across the metric like a CIDR and a SPICE in both the pedestrian and aircraft domain. So it was a summary of what I have achieved so far. What is the remain is we are going to, in the next chapter, discuss what is remain of my research. So let's look at what challenge I face and find during the publishing those papers and developing those components. I found that in the autonomous driving, we have an operational domain design concept, which is the core of the developing requirement engineering for autonomous driving validation or evaluation. So we find out that there are some incomplete ODD specification, lack of formal operational limit like a weather, behavior, cause unsafe AI decision in the autonomous vehicle. We plan to use the VREX to enable a structured benchmark against the RE-defined ODD boundary. Also, when we try to develop the CADE and this CADE, we find that there is some cross-modality misalignment. We're working on multimodal data, vision and text, and we see that there is a cross-modality and misalignment, semantic drift between the text and image, and sensor weakened AI understanding. We are planning to address this challenge also to improve the VREX, preserve the RE constraint across the modality via unified semantic alignment. Also, we find out the K in the K, if we have a human in the loop, we can have a better result. Static metric overlook the edge cases, expert input add the depths but need to structure also. Viscate support dynamic refinement while preserving RE semantics and usability. We said that this is our next system. So what is the next in the step? Trying to address those challenges. First, we are going to apply VREX for autonomous driving as a use case. As we mentioned, the challenge will lack of structured operational looping, causing unsafe AI generalization. Also, AI model learn from dataset, not explicit ODD. So we are going to plan to incorporate those ODD constraints in the development of AI. So solution ODD specification via VREX, define AI operational limit, for example, road condition, pedestrian behavior, benchmark the dataset and model against the structure RE constraint, and ensure real world validation through the systematic evaluation. So we hope that this impact the safe regulation, compliant AI decision making, and bridging the gap between the AI learning and real world constraint. Also, for gap aware multimodal AI, it is a matter because AI struggle with the modality gap, image, text, and textile misalignment between these modalities lead to information loss and bias in AI decision. Our approach is going to modality specific evaluation, identify, quantify modality gap consideration strategy. We have applies post hoc adjustment or learning based refinement, preserving semantic integrity by ensuring the structure RE benchmark guide the AI understanding. So we hope that this improves the generalization across the different data type, and having a multimodal AI remain aligned with the structure RE. So for human-centered AI dataset, we are going to address it in the VSK, is under process component. We are going to address the AI dataset validation is often offline, rigid, and leading to a static, non-interactive evaluation. Human expertise are also underutilized, so we can use that human expertise when they go through the data with a visual interaction. So also we wanted to introduce VSCADE as an interactive evaluation framework, visual AI dataset, to have a visual AI dataset evaluation, enable user to inspect, refine dataset and completeness, integrating AI for dataset benchmarking, helping expert understand the dataset gap and AI weakness, and having a real-time AI performance insight, bridging the automated benchmark with the human feedback. We hope it's help us to ensure datasets aren't just evaluated by a statistic metric, but are refined dynamically by domain expert, and enhance the trust, transparency, and fairness in AI dataset validation. So far I have published this paper. 5 of my paper got published. We submit another paper on the ODD, and we have 2 paper in hand, one in about the V-scale and other about the modality. Yeah. So that was my presentation. If you have any question and feedback, I will be glad to hear you.